So in the last class, we discussed about the registers, and in that we discussed about the shift registers and different types of shift registers, which is serial in, serial out, then serial in, parallel out, and parallel in, serial out, parallel in, parallel out. Those four different types of registers we have discussed in the last class. Now we have to discuss uh, another topic, which is the counters. And before we move to the counters, uh, I will explain some of the basics with the JK flip-flops. Okay, so some more information that you need to know before we go to the counter section. So in JK flip-flop, we know the truth table that we already discussed, the truth table of JK flip-flop. So that looks like, if you consider the truth table of JK flip-flop, this we already discussed this in the previous classes. So here we will be having, suppose you are having this clock pulse which is equal to 0. If your clock pulse is 0 and you are having JK as your inputs for your JK flip-flop, and Qn plus 1 is your next state. Okay. So if clock pulse is 0, your flip-flop is not active. So your J and K, which whether it is having 0 or 1 value, which is does not matter because your flip-flop is inactive. So when your clock is 0, this is a don't care condition. You don't have to consider these JK values. Anyway, this will be its previous state Qn. So Qn is the previous, Qn is the present state, and Qn plus 1 will be the next state. Okay. So you will be so this will be your Qn plus 1 will be your next state. And since you do not have this clock pulse right now, your clock pulse is 0. So J and K, you don't have to consider this J and K values because your clock is 0. So in any way, it is having the same state, same present state, because its state is not going to change because it is inactive when your clock is 0. And when your clock is 1, now your flip-flop is active. And in this case, you can have different inputs. For example, J equal to 0, K equal to 0. And in that case, we'll be having our present state, same state will be your output. So your next state will be equal to your present state because both of your inputs are 0, 0. So this way we already discussed these things by using that JK flip-flop diagram. That's why I'm not going to explain this again. I'm just showing this truth table for this JK flip-flop. So we will be having the same state when you are having J equal to 0, K equal to 0. And when you have this clock pulse which is equal to 1 again, you have, for example, J equal to 0, K equal to 1 state. And in that case, we will be having the state which is equal to 0. Next state, which is Qn plus 1, that is equal to 0. Because you are having K which is equal to 1, which is like a presetting condition. And then you have this clock which is equal to 1 and J equal to 1, K equal to 0. In this case, we will be having 1, output as 1. And the last condition, which is clock is equal to 1 and both this J and K are 1. And here we will be getting Qn bar, as your output, next output, which means that your Qn is the present state that is changed to its complement form, that is Qn bar, when you are having both j and k values are 1. And so this particular state is nothing but the toggling state, which means that if you are having your present state 1, for example, then that will change to 0. If your present state is 0, then it will change to 1. So this particular condition is called as toggling. Toggling means changing that output 1 to 0, 0 to 1. So present output or present state, which is changing to its complement form when you are having j equal to 1, k equal to 1, also the clock is also active or the clock is 1. So this is the truth table, and we already discussed that this two state we will use as a memory because it is not going to change, it is present state. And this state we will use for anything if you want to change the state from 1 to 0 or 0 to 1, then we can use this particular states. And this state we use as a toggling that is changing continuously with the clock pulse. Okay. So when you are having the clock pulse is high, that will change your output. And when it is going to low, it is not going to do anything with the output. Then again, when it is coming to high, that is maximum one value, when your clock is going to become maximum or 1 equal to 1, then again the output is going to change like that it will go. So that is the toggling state. Okay. Here when you are having this 1, clock is active and your k is 1, then your output will become 0. Okay, so present, if the present output is 0 or 1, it does not matter. Your output is going to become 0 when you are having this particular condition. And when you are having this condition, your output is going to become 1. It does not depend what is your present state. Okay. So these are the conditions, and this to be used to change the state of your flip flop, and this we use as memory. And here we use this we used as the storage. Okay? As we discussed when we discussed this JK flip flop, we discussed all these things. Okay, and we used this toggling state for your shift register. For the shift register, we used the toggling condition, that is clock is equal to 1, j equal to k equal to 1. And in that particular case, we will be having the present state, which is changed to its complement form. Okay. Now, if you consider the characteristics table of this JK flip flop, that we might not be discussed. Characteristics characteristic uh, table of JK flip flop. Okay, so let's discuss about this. So the characteristic table is nothing but if you consider the inputs like this Qn, J, K, and your next state Qn plus 1. So let's assume that your present state is 0 for these first four conditions, 0, 0, 0, 0. And your present state is 1 for the next four states, so 1, 1, 1. And Jk values will change 0, 0, 0, 1, 1, 0, 1, 1. Then again you have 0, 0, 0, 1, 1, 0, 1. So your present state, which is represented by this Qn, present state, and this Qn plus 1 is your next state. Okay, so present state is 0 in your flip flop, which means that I'm talking about state means we are talking about the output. Present output is 0. So when you are considering that JK flip flop, your present output is 0. Okay. and your j equal to 0, k equal to 0. And what will be the next state? In this condition, what will be the next state? That we have to discuss. So what we are discussing now is, suppose you are having this AK flip-flop, you're having J here, K here, and also you have that time clock pulse also. And then let's consider this as your Qn, and here we have Qn plus, sorry, Qn bar. So this Qn representing the present state. Okay, so that is that we denoted by this 0. So you're having currently your present state or present output, which is equal to 0, and your j equal to 0, k equal to 0 as well. Okay, so in that case, we can see that the condition from this truth table. You can check this truth table. So your Qn equal to 0, j equal to 0, k equal to 0. So you can see that j equal to 0, k equal to 0 here. Set this j equal to 0, k equal to 0 here. Okay. And your clock is, suppose your clock is active, which is clock is 1. And in that case, we'll be having Qn plus 1, which is also equal to Qn. You can see from here. So j equal to 0, k equal to 0, and your Qn plus 1 will be equal to Qn. So what is Qn? Qn is 0. So Qn plus 1 is 0. Similarly, again, you can consider, let's consider this case then. Okay, we can go one by one. So let's consider this case, 0, 1 case. Okay. So in that case, j equal to 0, k equal to 1, j equal to 0, k equal to 1. So that is this one, j equal to 0, k equal to 1. So in that case, what is Qn plus 1? Qn plus 1 is j equal to 0, k equal to 1. So Qn plus 1 is this one. That is 0. Qn plus 1 is 0. So Qn plus 1 is 0 here. Now next one is j equal to 1, k equal to 0. So in that case, the third one, k equal to 1, k equal to 0. In that case, we will be having this output 1 as your Qn plus 1. So this will be 1. And last one is both are having 1. So this j and k are 1. Then we will be getting Qn bar. That is the toggling state. Qn plus 1 is equal to Qn bar. So this Qn bar, you are having Qn which is equal to 0 here. So Qn bar is 1. So I hope you understood this. And the next fourth state, we are considering Qn as 1. Okay, as you can see from here, this fourth state. So we'll be having j equal to 0, k equal to 0 for that also. For j equal to 0, k equal to 0, your Qn plus 1 is Qn itself. So Qn is now equal to 1. So this is 1. And next state 0 and 1, 0, 1. So j equal to 0, k equal to 1. So we are getting, which is output is 0. And 1, 0, we are having output which is equal to 1. And for 1, 1, we are having toggling state. As you can see here, we have to consider Qn bar. And now our Qn is equal to 1. So Qn bar equal to 0. So this is the characteristic table of JK flip-flop. Now from this characteristic table, we will be considering the excitation table of JK flip-flop. So excitation table of JK. So in here we have to consider first input and outputs. So here we are considering inputs as inputs qn and qn plus 1. So this will give you what are the values, required values for j and k when you are having output your qn and qn plus 1 as you take the inputs. Okay, so that will give you that we will check here. So that qn plus 1 are the inputs, and here we are having j and k. You can draw this as a table and just bring it as a partition. So let's consider the four cases: 0, 0, 0, 1, 1, 0, 1, 1. So when qn equal to 0, qn equal to 0, qn plus 1 equal to 0, what is the values of j and k? So if you consider this characteristic table, you need qn equal to 0, qn plus 1 also 0. So these two, first is two values. Here we are having both qn equal to 0, qn plus 1 also 0, 0. So both of these two we have to consider. We have to consider these two. Okay, 0, 0. Qn is 0, 0 here. Qn plus 1 are also 0. So we have to consider qn 0, qn plus 1 also 0 condition. So we have to consider both these. So here we can see j equal to 0 for both of those cases, and k is 0 and 1. It is changing. So we do not have to consider k, because irrespective of the value of k, whether it is 0 or 1, if your j is 0, your qn equal to 0, qn plus 1 is also 0. Okay, I hope you understood this. Irrespective of your k value, whether it is 0 or 1, if your j equal to 0, if your j equal to 0, then your qn plus 1 and qn is, both of them are equal to 0. That is from this table. Okay. So then I can write j should be equal to 0. In both cases, we are having j equal to 0, but k can be 0 or 1. So I don't have to consider k values. So j should be 0. J should be 0. K can be 1 or 0, which means that I do not have to consider that, which is a don't care condition. We don't have to consider this k value. Now next one is qn equal to 0, qn plus 1 is equal to 1. So qn equal to 0, we have qn equal to 0 and qn plus 1 is 1. So these two we have to consider. In both cases, we are having qn equal to 0 and qn plus 1 is equal to 1. So in that case, we can, if we consider j equal to 1 and k can be either 0 or 1. So we do not have to, in this case also, we do not have to consider k values. It is a don't care condition, whether it is 0 or 1, it does not matter. If your j is equal to 1, we will be having qn equal to 0 as well as qn plus 1 is 1. So we can write in that particular condition, our j should be equal to 1 and k can be 0 or 1. So it is a don't care condition. It does not matter. And in third one, we have qn equal to 1 and qn plus 1 is equal to 0. So this condition, qn is equal to 1, qn plus 1 is equal to 0. Oh, here we have some difference, right? Yeah, in that case, we have to consider alternatively. So let's take another pen here. Let me take another pen. So this one, so that is qn equal to 1 and qn plus 1 should be equal to 0, right? So okay, so then I have to consider this one. This one, this 0. So qn is equal to 1, qn plus 1 is 0. Here also we are having qn equal to 1, qn plus 1 is equal to 0. So now I have to consider these two sets, this one as well as this. So here you can see the j value is changing, j equal to 0, j equal to 1 here, but the k value is 1. So if your k value is 1, And irrespective of this j value, we are having this condition qn equal to 1, qn plus 1 is equal to 0. Okay. So here what we need, your k should be equal to 1 and we do not have to consider j. So here k should be equal to 1 and j is don't care condition. And the last condition, this one, that is both are having equal to 1, that is qn equal to 1 as well as qn plus 1 also 1. So this is qn plus 1 equal to 1, qn is also 1, this condition. And here also we are having qn equal to 1, qn plus 1 also 1. So these two set of values of jk, we have to consider. This one as well as this. So here also we can see j value is changing 0 and 1, but k value is fixed. So k value should be equal to 0. So under that condition, we will be having both qn and qn plus 1, which is equal to 1. So that here we do not have to consider j again, but this k value should be equal to 0. Now, if you make the truth table for this, then we have to consider truth table, sorry, k-map. If you are making k-map for this, then we have to consider a two variable k-map. So here we have to consider qn plus 1, this side, qn plus 1, here it is qn, and it can be 0 or 1, and 0, 1 here. Now we have to consider qn plus 1 is 0, qn is equal to 0 condition. And there we are having, for example, if you consider it for j, so I'm considering this table for j. So if you consider for j, then in the first cell, we will be having, if you consider qn equal to 0, and qn plus 1 is also 0. So we have to consider this particular value, that is 0. Okay, so first column we are having this 0. And second one is 0, 1. Okay, that is qn 0. Qn plus 1 is 1. So that we are having j value is equal to 1. So we are having 1 here. That is qn plus 1 is 1 here. Qn is equal to 0. And the third one, qn is 1. Qn plus 1 is 0. So that is this cell, this particular cell. So there we are having this don't care condition. Again, we are having 1, 1. Qn plus 1 is 1. Qn is also 1. That is this cell. And that is also don't care condition for j. Similarly for k, if you consider the k map, if you draw the k map, then we can draw it like this. Here we are having qn plus 1. Here we are having qn. And let's do variable k map. So 0, 1, 0, 1. So when qn equal to 0, qn plus 1 equal to 0, k values don't care condition. So this one, first one is don't care condition. This is don't care condition. And next one is also don't care condition. Here we are having 1 and the last one is 0. That is for k. And if you simplify this for the expression for the j and k values, then we can group these two with the min terms. You can see 1 grouped with the don't care condition. If you group with the don't care condition, then you can minimize, you can get the minimal form. Okay. If you take this only this cell, then you will not get the minimum form or minimized form. So that we have to increase the number of elements in that particular group, or the group size we have to increase. So we are making it a double, so that we'll get the final expression for j, which is equal to, what is this? This one is this is qn plus 1, right? Qn plus 1. What is common in that? Qn plus 1 is common. Qn is changing. Qn is changing from 0 and 1. You can see from here, but qn plus 1 is same 1. So this is nothing but j equal to qn plus 1. And here, if you consider the same scenario, then you have to group it like this, these two, and you will be having k, which is equal to qn plus 1 bar. Because you are having qn plus 1, we are considering this part, so it is 0 here. Okay, qn plus 1 value is 0. And if you take this grouping, and you are considering this 1, that is a min term, and then you have to consider qn plus 1 bar, because in that particular form, we have to consider qn plus or a bar as your 0. A equal to 1 and a bar as 0 when you are considering min term. So when you are considering this 1, that is min term, when you are considering that, you have to consider a bar as 0 and a as 1. So in this case, we are having 0, so we have to take qn plus 1 bar. That is your k. So these are the expression for this j and k when you are considering the jk flip flop. Okay, so that's why we are considering when you draw that jk flip flop, then we are taking the values. I hope you know these things. Suppose you are having input j here, okay, and k here, and we are having some connections inside, as you know. So I'm not going to draw all those things. Something inside, some connections, as you know, two NAND gates, four NAND gates are there, and we have taken like this and all those things. Okay, and all those connections will come within this box, for example, and we have taken the output. I'm interested in this output part. Okay, so we have taken the input j. We have taken from here like this to this first NAND gate. So you can draw it like this for first NAND gate, and then we have considered from here to this one. Okay, so that connections are coming from this particular table. After reducing this expression, after finding out the expression for j and k, we are considering those connections. What will be the value of j and k when you are having when you are considering the q and qn plus 1 as your output. So qn plus 1 is your j, and qn plus 1 bar should be your k values. So when you're considering this jk flip flop. Now, if you consider, now we will move to the counters, and we need this particular expressions or this kind of a simplification method in there. That's why I'm explaining these things now. So now we'll move to counters. I don't know whether you have you studied these counters before or not, but anyway, we'll discuss that from the beginning itself. So counters, as you know, these counters are sequential circuits that counts the clock pulses. Okay, basically we use this to count a particular event that happened in a particular digital circuit. So this, as a definition, you can write this as a sequential circuit, a sequential circuit. Sequential circuit means it depends on your on the memory element or the previous state of your circuit. Okay, so that memory depends on that previous state. I hope you know this sequential circuit. Okay? So sequential circuit is nothing but the circuits that depends on your previous state. So a sequential, so the counters are a sequential circuit that uses we can say that used for sequential circuit that used for, or you can write that can be used. Okay. A sequential circuit that is that can be used for counting pulses. So that can be used for counting pulses. So different clock pulses you can count, or pulses you can count. If you are having such a circuit, sequential circuit, then that particular circuit is called as a counter. Okay, and basically we can classify these counters as synchronous and asynchronous counters, types of counters. Broadly, we can classify them as synchronous and asynchronous counters. And this asynchronous counter we can also refer as ripple counter. This also we can represent as ripple counter. So in synchronous counters, we have different some difference between this synchronous and asynchronous counters. So here, first point is that the clock is given clock is given to all flip-flops. Here clock is given to only, I can write, given only to the first flip-flop. So here we can say flip-flops are clocked simultaneously. Here flip-flops are clocked. Then we can say that are not clocked simultaneously. So here we have simultaneously clocked simultaneously. Flip-flops are clocked simultaneously. Here we are not having these flip-flops are not clocked simultaneously. I will you will understand what is what are the meanings of these particular explanations. What that means is that if you are having these counters, suppose you are having a flip-flop here, suppose you are having two flip-flops here, and if you have clock like this, okay, applied clock like this, which means that you are applying clock to both these flip-flops. Let's say this is flip-flop 1, this is flip-flop 2, and you are applying for this both these flip-flops, you are applying same clock at the same time. Okay, so both are getting the clock pulse at the same time or simultaneously, and this is the this type of counters. If the counters are having this kind of setup where you are having the clock pulse which is applied simultaneously to all the flip flops, then which is called as a synchronous count. Okay, and in some cases, the clock will not be applied to all flip flops at the same time. We'll show that. Suppose if you are having some connection like this, if you are having second flip flop here, and the clock for the second flip flop is taken from the output of the first flip flop, like this. So in this case, the clock is not applied simultaneously for both the flip flops in that particular network or circuit. And in that case, it will be called as an asynchronous circuit or asynchronous counter if you are considering it as a counter, because the clock is not applied simultaneously on both these flip flops. So obviously, because of this, if you are applied clock like this, then this circuit will be slow because it has to execute operation in the first flip flop. Then only this second flip flop is going to become active. So it will take some time. First flip flop output is required for as the clock of the second flip flop. So the second flip flop has to wait for the output of the first flip flop, so that it will take some time to get the total output of this second flip flop, okay, or this total output of this circuit and their circuit. So in this case, asynchronous counter, we are not giving the clock pulse simultaneously to all the flip flops, so that this particular asynchronous counter will be low. So the speed is low, or it is low speed, and here we are having high speed. Why it is high speed? Because we are simultaneously giving clock pulse to all flip flop at the same time. Okay, simultaneously giving clock pulse to all flip flops, which means that we are applying clock pulse to all flip flops at the same time, so that all the flip flops will be active at that particular instant itself, so that it will be fast. Here we are not applying clock pulse simultaneously, so that the second flip flop has to wait for the output of the first flip flop. And if you are having n number of such flip flops, then each of them have to wait the output of the previous flip flop to active, okay, to get activated, so that it will take some time for total execution of that particular circuit as compared to the synchronous counters. So it is speed will be low. Okay. And the circuit, if you consider circuit, here the circuit will be circuit is complicated as the number of flip flops increases. Here circuit will be, I am writing CKT for circuit. Circuit is simple. So for for synchronous counters, we are having a complicated circuit when you are having large number of flip flops, because you have to connect clock pulses to each and every flip flop, and that makes the circuit more complicated. But here we have to take the output and given to this next flip flop, so the circuit will be much more simple as compared to the synchronous counter. Okay. And here we are having, for synchronous counters, random counting is possible. Random sequence counting is possible. I will explain what is meant by this while taking the synchronous counter examples. So this is random counting, sequence counting is possible. Here fixed count, fixed count sequence is possible. Only you can write. So so here random count sequence is possible. Here fixed count sequence is only possible. Fixed count sequence only for is possible. Or you can write there is some rearrangement is required for this sentence also. So here you can add only fixed count sequence is possible. Here we are having random count sequence possible. Here only fixed count sequence is possible. So counting, as you know, counting means 1, 2, 3, 4, etc. like that. If any event is happening, then here you can count like 2, then 4, 6, some other value. Okay. So for example, some 2, 4, some 8, some 15, some 22, like that. So random counting is possible here. But here we can have some fixed count sequence like 1, 2, 3, 4. Okay. So the counting is fixed. The counting sequence is fixed. It is not random numbers here. So that we will explain when we are explaining some examples with this synchronous and asynchronous counter. In there we will explain it in more detailed way. So these are the basic differences between synchronous and asynchronous counters that we just discussed. Okay. Now we will just look at the synchronous counter first. Okay. So I will explain one for synchronous counter. I will explain how we can design a synchronous counter. What are the different steps required for this particular process and all those things. And if you consider any counter, the mode of the counter, mode or modulus of the counter means the number of states passed by the counter before going to its original or initial state, we can say, before going to its initial state. So mode or modulus of the counter means that the number of states passed by the counter before going to its initial state. Okay. For example, if you consider a counter which can count up to 3, so in that case we are having 0, 0, 0, 1, 1, 0, 1, 1. Okay. So in this particular case, we need 2 flip flops because we have to consider 2 values here 0, 0, 0, 1, 1, 0, 1, 1. Both we have to consider. Okay, and if you consider this particular case, this is corresponding to 0, this is corresponds to 1, this corresponds to 2, and this corresponds to 3, decimal equivalent of these binary values. Okay. I think yes. So this is your first output, for example, Q0, and this is your second output, Q1, for example, I'm saying. Okay, so this is the output of first flip-flop, JK flip-flop, and this is the output of the second JK flip-flop. So we need two flip-flops to store these values. In each time, for example, the first flip-flop will be storing this 0, and the second flip-flop is storing this 0, and you will be getting total value as 0. So the counting will be 0, 1, 2, 3, etc. like this. Okay, it can be up counting or down counting. It is also having this classification. The counter can be up counting or it can be down counting. It can be a up counter or it can be a down counter. Up counter means the progression will be 0, 1, 2, 3 like that. If it is down counter, then it is from the highest value 3, 2, 1, 0 like that. Okay, so that is another classification, up counter or down counter. So in this case, we are considering, if you consider 0, 1, 2, 3 as the counting happening. And in this particular case, you can see there are four states possible, for the counter. This is the first state, second state, third state, fourth state, and the fifth state will be again 0, 0. That will give you again result 0, 0. That is 0. And the sixth one will be 0, 1. That will give you again. So this sequence continues. So the modeless or mode of this particular counter means that the number of states passed by the counter before it is going to its initial state. So this is the initial state, as you can see. The initial state is in this particular counter, which is 0, 0. So this is the initial state, and it is repeating its initial state in this particular after this clock. Okay. So for example, if you consider the clock at like this, we're applying this clock here. So at this clock, it is repeating its initial state. So up to that, how many number of states it is passed? So we are having first state, second state, third state, fourth state. Then it is repeating, which means that it is again going to its initial state. So this particular counter is having four states. And this is given by your mode of your counter. So this mode, which is denoted by letter capital N, and this capital N should be less than or equal to 2 raised to n. For any counter, if you consider, should be less than or equal to 2 raised to n. And in this particular case, you are having the mode, which is maximum mode, that if you are considering 2 flip-flops, then you will be having maximum number of modes, which is equal to 4, 2 raised to 2. Anyway, it should be less than or equal to 2 raised to n. For any counter, should be less than or equal to 2 raised to n. Now we will go to the synchronous counter. We will discuss what are the different steps you need to form or to make a synchronous counter. So here we have, first we have to consider how many number of flip-flops you require, okay, number of flip-flops, and also type of flip-flops. So the first step is the number of, so we are talking about synchronous counters. So I'm discussing this for synchronous counters only. I don't know whether this is that much important to you, but this is how we form this synchronous counter. This may not be that much important to you. So synchronous counters. For synchronous counters, first we have to consider or decide how many number of flip-flops or what is the mode of your counter that we have to consider. And so that for that we need to decide number of flip-flops and type of flip flops. What type of flip flop you require for this particular counter? So type of, you can use JK flip flop or T flip flop, etc. for you to uh, design this particular counters. So first we have to decide the number of flip flops required, and that is depending on your mode of your counter, whether you need 4 mode, mode 4, or mode 8, or like that. So what mode your mode 5 counter you require, you are going to design. Depending on that, we need to decide the number of flip flops required for that particular circuit. And also we need to know what type of flip flops we need, whether it is JK flip flop, T flip flop, D flip flop, and all those things. That also we have to decide. Okay. And now let's consider a 2-bit example, or we can go first with the steps. Okay. And the second step is the excitation table formation. Excitation table for the flip flops. And third step is to draw the state diagram. State diagram. Okay. And the fourth one is the obtaining the Boolean expression. Obtain the Boolean expression. And the last one is draw the circuit. Draw the circuit diagram. So these are the different steps required to design a synchronous count. Okay, let us take an example. As an example, we can consider a 2-bit synchronous counter. Example, 2-bit synchronous counter. So how many number of flip flops required for 2-bit? 2-bit means 2-bit, which means 2 flip flops. 2 flip flops required because 1 flip flop can store 1 bit of information. So we need 2-bit synchronous counter, which means that we require 2 flip flops which can store 2 bit of data or 2-bit information. Okay, so we need 2 flip flops, and let's consider JK flip flops. So we require, so it required 2 JK flip flops. Now we already decided the number of flip flops and types of flip flop that required. So 2 JK flip flops required for this 2-bit synchronous counter. Okay, now excitation table. Next step is excitation table. Excitation table for the flip flops. So for both these flip flops, we have to consider the what is the excitation table. Okay. So I'm just writing the excitation table for JK flip flop here, just representing that we just discussed. So PS and NS, which means present state and next state. Present state is Qn, next state is Qn plus 1. Okay. And this is for JK, 1 JK flip flop. Okay. So this is 0, 0, 0, 1, 1, 0, 1, 1. But for the values of JK correspondingly, JK for this particular states. So we'll be having for this, write it here. So let's consider J here, K here, So JK, what are the conditions? 0, don't care. 1, don't care. Here, don't care. 1, don't care. 0. That we just discussed just before. Okay. So this is a truth table for JK flip flop. But in this case, we need two flip flops, two JK flip flops. This is for the case of the excitation. Sorry, not truth table. This is the excitation table for JK. Okay. Excitation table for JK. Okay, for in our current case, we need excitation table for two flip flops. Okay, so let us consider it like this: present state, and in the present state itself, we are having Q1 and Q0. That is, for Q0 is the first one, first flip flop output. Q1 is the second flip flop's output, and we are having Q1 and Q0 for present state itself, and then we have next state. Next state we are having. Similarly, we are having Q1 and Q0 in that also. Q1 and Q0 for next state. Q1 and Q0. Okay. And also we are having the inputs which are J1 and K1. So these are our outputs. We have inputs which are J. So we are having J1, K1, then J0, K0. So J0, K0 is the inputs of first flip flop, and K1, J1, K1 are the input of second flip flops. So the first state will be coming like for the case of this counter, first state will be 0, 0, as you can see from this state diagram. So it is this state diagram you can see this is the third step, I think. Okay. So from state diagram, we are having 0, 0, 0, 1, 1, 0, 1, 1 as your states, different states of your counter. Okay. So first it will be 0, 0. Then I have to take 0, 0. Then I have to take 0, 1. Next state is 0, 1. Okay. Now my present state is 0, 1. I have to consider 0, 1. Then next state is next state will be 0, 1 and right 0, 0, 0, 1. Then 0, 1 is my present state. Then next state is 1, 0. Right. Now 1, 0 is my present state. Next state will be 1, 1. And from this 1, 1 is my present state. And my next state will be 0, 0. So once it reaches this 0, 0, now it is again repeating in the same procedure. So it has maximum 4 states. So 4 states are achieved. Now that we represented by using this state diagram. Okay, 0, 0, 0, 1, 1, 0, 1, 1. Once it is this counter reaches 1, 1, then it comes back again to this 0, 0. Okay, so this particular case is not needed here. So in state diagram, we are representing these different states available for this particular counter, and we are having 2-bit counter, or we can say it is a mode 4 counter. Okay, mode 4 counter. So in that case, we will be having 4 different states: 0, 0, 0, 1, 1, 0, and 1. And that I have represented here, Q1 and Q0 correspondingly for present state. For present state, we are having 0, 0 first. Then for the next state, it will be 0, 1, because it is going from this 0, 0 to this 0, 1, like this. Then from that, so now this is my present state. 0, 1 is my present state. And from 0, 1, it is going to 1, 0. That is my next state. As you can see from this state diagram, it is going from 0 1 to 1 0. So that is my, so this is, so at first this is my present state, and then it is going to the next state 0, and then this will become my present state, and next state will be this 1 0. So the, in that way we have to fill this particular column q1 q0, and from that we will get this condition that you can easily get from this table. When you are having q1 equal to 0, here also we are having this next state also q1 equal to 0, so we are having this 0, and then you are having this 0, q1 equal to 0, next state we are having this 1. Okay, so 0 1 will give you a value which is equal to 1 here. So this is 1, and then 1 0 will come, sorry 1 1 will come, because q1 is 1 in the present state. In the next state q1 value is 1, so 1 1, for 1 1 we are having this don't care condition that is coming here. Yes, so and this one, last one is 1 0 1 0 1 0 is for this don't care condition that is coming here. And then for k1 also similarly you can do the same procedure. So for k1 we are having we have to consider q1 again for the case of k1. Okay, so for k1 we are having first consider q1 equal to 0. We'll just take another color here. So q1 equal to 0, and this q1 is also 0 for k1. So 0 0, for 0 0 k1, this is don't care condition. So first don't care, which will be coming as don't care condition, and then we are having the second case which is 0, q1 equal to 0 and q1 equal to 1. 0 1 0 1 is giving the next don't care for k, that you can write like this, and then it is coming 1 1 for q1. So 1 1 corresponding to 1 1 we are having 0 for this k, so we are having this 0. So and then last one is 1 and 0. For 1 0 we are having k value which is equal to 1, so that 1 is coming here. So this is how it is table is coming. So I made a mistake in the first case. Okay, so for similarly for J0 also we can do the same procedure. So J0 we can see 0 0 first. Here it is 0. Sorry, this in this case it is 1. So 0 1 will come first. We have to consider Q0 values for J0 and K0. So Q0 is 0. Here next state Q0 is 1. So 0 1 combination we have to take. So 0 1 combination is this one. Okay. So 0 1 combination, for 0 1 combination we are having J value which is equal to 1. So we are having this first 1 value, and then we are having next value is 1 and 0. So for 1 0 we are having this particular combination 1 0, then that will give me J value which is don't care condition. So this one I have to take don't care condition. So I will take don't care condition. And the next one is for Q0. Next one is 0 here and 1 here. So 0 1 I have to consider. So again this I think this Q0 we have to consider this Q0. Yes, 0 and 1. So 0 1 if you are considering I think 1 1, yeah, 0 1. So 0 1 where it is coming, this one. This one for this J, again I have to consider this same set 0 1 this one, then again I am getting this one, and the last one is 1 0. Okay, 1 0 again which is coming, so it is again a don't care condition. Similarly you can also work out with this K0. You will get first don't care, then 1, then don't care, and 1. Okay, and from this we have to formulate that K-map in order to find the Boolean expression. So I will do that here itself because it is, so this is the fourth step, right? to get the Boolean expression. So for fourth step, we are having this particular K-map, and from this K-map, we will find out what are the values corresponding to these different inputs that we are looking at. So we are having Q0 here, Q1 here, 0, 0, 1, 1, and for two cases I will show here how it is coming, and the remaining two you can do by yourself. So we have two variable K-map. So here we are having Q1 and this is Q0. So when you are considering J1, you are having the first value which is equal to 0, that is for 0, 0. So this is 0, 0. And next one is for 0, 1 case. So 0, 1 case, this one. Okay. How this 0, 1 and 0, 0, all those things are coming? It is coming from here. If you are considering this as your first case output and this is your next output. Okay, so okay, I should not like this because I had to take in the reverse order, right? So first we had to consider Q0, then we have to consider Q1. So it should be reading as Q1, Q0. So in this table, it should be 0, 0, 0, 1, 1, 0, 1, 1. Like this, it should be counting. So we have to consider this particular output Q0, particular output Q0, and this particular output Q1. And we have to take it like Q1, Q0 like this. Okay, so this is the least significant bit again, and this is the most significant bit. Okay, so now if you consider the second one, that is this one is 0, 0. Q0 is 0, Q1 is 0, so 0, 0 will get. And next one is 0, sorry, next one is this, here it will be 1. So next one is here it is 0, so 0, 1 will come. Okay, so for that we have to consider Q0 as 0 and Q1 as 1. Okay, don't confuse with that. Q0 is 0 and Q1 as 1. So in that case, we are having the third value. So this will be don't care condition. So that is representing the third state. So the third state we are having here, that is don't care. And this particular column is for Q0, Q1, we can say this is 1, 0. Or we can read it in the other direction. Let's first consider Q1, then Q0. So it will be 0, 1 in this case. So Q1 has to be 0 and Q0 has to be 1. So Q1 has to be 0, which means that this one, and Q0 has to be 1, right? So this particular case is for second case. So this one I am taking, second state. So I will be having 1 here. And the last one, we are having Q1 equal to 1, Q0 also 1. So that is the last state. So that is again don't care condition. Here also we are having 0, 1, 0, 1. So first case we are considering Q1 equal to 0, Q0 is also 0. That is first condition, first state. So for first state we are having K1 equal to don't care condition. This one I am talking. And then the second case we are having Q1 is equal to 1, Q0 equal to 0. So that is this one. Okay, that is third state. Third state means we are having 0. So this one will be equal to 0. And then Q1 equal to 0, Q0 is 1. So this second one, this one. So that is Q1 is equal to 0, Q0 is 1. So that is second state. Second state, we are having this don't care condition. So this is don't care condition. And the last one is 1, 1, obviously. So that is 1 here. This is 1. Similarly, you can formulate the other K-maps for J1, K1, J0, K0 also. Okay, so from this, how we can reduce this K-map by using grouping? We can group these two. I am using min terms, and I am considering this one, and I can group that one with this don't care condition, considering this don't care as one. Okay, that we already discussed while doing this K-map explanation, all those things. So this from this we can get this expression for J1, which is nothing but Q0 for common in this particular group, which is Q0, because I'm considering the min terms. So in min terms, 1 means Q0. Okay, 0 means Q0 bar. So now I am having this group which is common to this Q0. So I am taking J1 as Q0. That is the simplified expression for J1. And for K1, how I can group? For K1, I can group it like this for min terms. So for min terms, we are having this group, 1 and this don't care condition. And this in this time, I'm considering this don't care as 1. Okay, as you know, this don't care, we can consider 0, either 0 or 1 according to our convenience. So this in this time, I am considering this don't care as 1, and we are grouping these two cells. So we are getting the common term as again Q0. This again will give me Q0. So these are the expression for J1 and K1. I am having Q0 for both. And similarly, I can reduce K-map corresponding to this J0 and K0, as you can see from here. So from here, I will be getting expression for J0, and J0 will be, I have to group here also. So I have to make the maximum possible group. So I will group this whole, because I can consider these don't care conditions as 1. So I can group them all together. That will give me, so this will give me J0 equal to 1. If you are grouping all together, then that means your J0 is equal to 1. So that is maximum possibility that you can have with this two variable K-map. You can group these 4 sets. Okay. In such case, we will be having maximum the variable value which is equal to 1, because you are considering min terms. And here also we can group them all, because we are having 2 don't care cells and 2 cells with value 1. So we can group them all together, and that will give me K0 also equal to 1. Okay. So for this synchronous 2-bit counter, if you're considering this, the 5th step is, as you know, 5th step is the design. Okay, that is nothing but the circuit diagram. Yes, this one is circuit diagram. So for circuit diagram, we are having 2 flip-flops, 2 JK flip-flops. Okay. And for this 2 JK flip-flops, we have to consider inputs as first 2 inputs are J0 and K0. And the second flip-flops are having inputs J1 and K1. Okay. And here we are having Q0. This one should be Q0 bar. And here we are having Q1. One should be Q1 bar. Now we have to do the connections. So as you know, for this synchronous case, we have to apply the clock pulse for all the flip-flops simultaneously. So we'll give clock pulse to all the flip-flops at the same time. Here also we are having same clock pulse applied to all flip-flops. So here we are considering 2-bit counter, so only 2 flip-flops are there, and we are having this clock connected here. Okay. Now what is J1 and K1? What is J1 and K1? We already did find out. We found out that J1 and K1 which are equal to Q0, right? That we did for from this K map. As you can see from here, K1 equal to Q0, K1 is also Q0. Okay. So that we have to give in this diagram. So J1 equal to Q0 and K1 equal to 0, Q0. So how it will come? So I have to take from this Q0, I have to directly connect to this J1, as well as I have to connect it to this K1. So K1 equal to Q0, J1 also equal to Q0. Now what is J0 and K0? J0 and K0 are 1. J0 and K0 are 1. This also we found from this after simplification of that K map. So that we will get K0, J0, 1. So I will just give here my pulse. Here J0. This. Okay. So I had to connect this to K0 also. So this one is maximum value, that is 1. This one is 1. So this is how this diagram of 2-bit synchronous counter should be. So this is logic 1, and your output is Q0 and Q1. So Q1 you can take from here. This is your Q1, and Q0 you can take from here. This is Q0. Okay, so this is how we design the synchronous counter. So this is just an explanation how we can initially how we can formulate all these expressions or the Boolean expressions for the inputs and outputs of all those flip-flops, how we will end up with this kind of a diagram for the counting purpose. Okay, so this is not that much important for your case, but this is the basics of the counter, how we can how we are coming to this particular diagram for synchronous and asynchronous. Similarly, we have asynchronous counters also. We will discuss it later. So here we are having the circuit diagram for a synchronous 2-bit counter, or we can say mode 4 count. Okay. So from here, if you are considering this particular circuit, let us consider the operation of this circuit. And this is logic 1, and you are having clock which is enabled now. Okay, which means that we are having that inverted or the negative triggering. At that particular point, it will be uh, changing its toggle state. Okay, that state will be changed. Toggling happens at that particular uh, negative edge of your clock pulse. So let's consider what will happen if your logic is equal to 1 and your clock pulse is uh, coming. So let's consider initially both Q0 and Q1, Q0 and Q1, which are at 0, 0, they are not having any value. So that is 0, 0. Okay, so initially we are considering Q0 and Q1 as 0, 0. And when you are having that first negative edge of your clock pulse comes, this flip-flops, let's consider this flip-flop 1. This has your flip-flop 1 and this is your flip-flop 2. So when the clock pulse comes, this flip-flops will change its states, as you can see, as you know. So this particular 0 in here will be changed to 1, and this particular state Q1 that also will be getting changed. But here, as you can see, this one is Q0 initially. Okay, so this 0 will be coming here. Okay, so since this J1 and K1 are now 0, the toggling will not happen. Okay, so this Q0 will change. Okay, I will write this Q1 first because it will make confused. Okay, so because when you are writing that, it is better to write Q0 at the end because it is the least significant bit, Q1 here. So Q0 will change to 1, but Q1 remains as such 0 because this J1 and K1 initially it is 0. Okay, so the JK flip-flop is not toggling because the input J1 K1 should be equal to 1, and then only it will do that toggling process. As you know, this the JK, when you are having J equal to 1, K equal to 1, and your clock is also enabled, means that your clock is in the negative edge. Okay, and at that time only we are having that toggling condition. But in this particular case, we are having this J1, K1, which are 0 because your Q0 is 0 initially. Okay, so this will not make any toggling in this particular flip-flop 2. Okay, so Q1 remains as such 0 and Q0 will be 1. But in the next clock pulse, what will happen? Your Q0 is now Q0 equal to 1. This one will be going through this connection and it will reach into this J1 and K1. Now your J1 and K1 are 1. Okay, and this already 1, J0 and K0 is already connected to this logic 1. So both flip-flops will be toggling. So this will become 1 and this will become 0. And for last pulse or the fourth pulse, I will draw it like this. So this is second negative triggering and third one is this. And for the third one, we are having Q1 equal to 1, Q0 equal to 0. So now here Q0 equal to 0. Okay, so that is connected to this J1 and K1. Now your J1 and K1 are 0. Okay, so your Q1 will not change. So Q1 will not change now. So it will be 1. But Q0 is going to change. Q0 will change from 0 to 1 because it will toggle for the next clock pulse. So it will change from 0 to 1. And in the next clock pulse, for the negative edge, we will be having again that Q0, we are having now Q0 equal to 1. Okay, so that one will come to this J1 and K1. So this Q1 value will toggle now because J1 equal to K1 equal to 1 and clock pulse is at the negative edge triggering, negative edge. And so this one will be toggled to 0. It will change to 0. And at the same time, Q0 is changing to 0. Now you can see that this state is already there. So this state is already there as your initial state. So after these four states that you are having, the same state repeats. Okay, so these are your four states that you can have with this particular counter, and it will repeat if you are increasing the time pulse. If you are having more pulses, clock pulse, okay, then it will continue in the same fashion 0 1, then again 1 0 1 1, again 0 0, like this. So that repeats. Okay, so this particular number of states, okay, this number of states by which before the counter repeats its original state or the initial state, which is called as the modulus or mode of your counter. Okay, I will repeat it. The number of states passed by the counter before going to its initial state, and which is called as modulus or mode of your counter. Okay, so in this case, number of state passed by the counter before its initial state is 0 0, that is nothing but 4. Okay, before its initial state it is 4, so 4 states are possible with this counter. That's why it is called as mode 4 counter. Okay, and if you are considering the decimal equivalent of this, decimal equivalent of this will be, this one is 0, and this one is 1, this one is 2, this one is 3. You are calculating decimal equivalent. How you can calculate that? For example, if you consider the last one, 1 into 2 raised to 0 plus 1 into 2 raised to 1. This is your decimal equivalent of this binary digits. So this will be giving you 1 plus 2 raised to 0 is 1, 1 into 1 is 1, and 1 into 2 raised to 1, 2 raised to 1 is 2, that is it's 2. So this will be 3. So this is how we'll convert from this binary to decimal. So we are having this kind of a progression. So with the time pulse, we are having a counting like 0, 1, 2, 3 in this fashion. 0, 1, 2. So when we are having this kind of counting that is progressing, okay, or it is increasing its decimal value, which is called as up count. Okay, so this is a 2-bit up counter. This is, we call it this as up counter. So this is a 2-bit up counter. Now how we can convert this particular up counter to down counter? Okay, that we will discuss when we do the asynchronous counter, which is much more easier. So here we can see that this 2-bit, with this 2-bit counter, we can count up to 3. Okay, 3 pulses we can count, and then that will repeat by itself. Okay, because it is having only 4 states.